You're live.
Okay, so today is going to be the session number 2 of Anomaly and Novelty detection. Today, we're going to cover some classical model for detecting an anomaly. So this section, I'm just going to kind of as a something that you should remember that all the model was either supervised, semi-supervised, and unsupervised. So I'm going to repeat all these concepts again. And the thing that we're going to discuss today will be mainly about some semi-supervised and unsupervised one. And today, as I said, is going to be about classical machine learning based approach. So today we'll basically mainly talk about the models, kind of prior to deep learning models that you can use to find some maybe boundary around your data, or you can kind of distinguish anomaly from your data. So there are lots of algorithm that has been developed in past couple of years or decades that all of them can be useful for this particular task. So as I said today, first I will try to cover isolation forest, which is one of the powerful models, which is like its category would be like ensemble techniques that is using like a ensemble of models to be able to find an anomaly. The other one is one-SVM, which the category of that one would be one class classification. And the third one is clustering techniques that we will use. We will see how clustering can be helpful here. And lastly, I will talk about self-supervised models, that how can we use that kind of new concept. So how can we use it to be able to learn our data and then for sure be able to say what is not normal in your data set. So first thing first, it would be what is isolation forest or Iforest. The building block of the Iforest algorithm is a decision tree. It's a tree that at each step pick a feature and make a decision based on it. Like here, it would be if at the first level, it would be if let's say weight is more than something or less than something. So it will divide or split the space. And it, because splitting a space would be kind of like equal to having like a node in the tree that you are making a decision. You're saying that if the value is more than that predefined number, you go left or you go right based on like it can be like you can see it as like a if else condition. So the whole idea is you can kind of like split the space, and each level you're making a new subspace in that area. So here at the first level, you are dividing the space based on weight, and the next and in the second level, it's dividing the space based on the year. So it's saying that if year is more than, let's say, 77.5, divide into the two space, and then you will have maybe kind of like a 3 space in your data set. This entity has been used for classification mainly, or even you can use it for regression. But the thing is, isolation forest is used in different way. So even so isolation forest follow basic principle of decision tree, but it's try to separate each point in the data. So it's not trying to split two class. It's try to split the data enough so it can isolate each point, each sample in your data set. So decision tree so if you can so the idea is like build decision tree to see how many random split on random features it takes to isolate each data point. And the number of splits required to isolate a sample is equal to the path length from the root node to the final node. So it means, let's say if you want to isolate one of the node, you have to split the data enough in different features randomly, so you can isolate a node. And then that would be kind of the definition of it would be in the decision tree would be a path from the root to that node, and then we could call it like a path length. And these algorithms take advantage of the fact that anomalies are the minority data point, that they have some attribute and value that are very different from those of normal instance. So they will be kind of far from them, and the isolation tree should be able to easily separate them from the rest of the data. So you can say easy to isolate point, which maybe will have the same concept as maybe low density ones, are considered anomalies, and tightly packed ones are normal. And so the shorter the path, you can say the more anomalies the point will be. So the whole idea is like here is like random partitioning produce like a shorter path or anomaly. So it means like if I randomly select feature and randomly cut them in different way, so the whole idea of isolation tree would be that those anomaly will have shorter paths to the root than the normal one, because we are saying that normal one will be packed together. So dividing them and isolating them would be harder for the model. So that's kind of the idea of isolation first and isolation tree. And if you want to see an example, let us take an example here first. So if you have 2 dimension or 2 feature, x1 and x2, isolation first will create a split on the value of x1 and x2 to isolate the points. So it can be seen from the picture that a normal point n is isolated by having multiple split on both feature x1 and x2, and the path length will be super long. However, an anomaly point like A is isolated by just one split on x1. So a higher isolation score is assigned to A compared to n, because they're saying that because A is like super sparse, maybe in a like a lower density area of the data set. So you should be able to easily isolate it by some like a random cut in your data. And what is isolation forest then? So isolation forest is basically an ensemble of isolation trees, and each tree is an like isolation tree which is constructed from like some small subspace, and each tree isolates every instance from the rest of the instance in a given sample. And so these three isolate every point, and this path and the path length will be the average over a forest of such random tree. So it means that basically the isolation forest will make lots of those like those isolation tree, and then for each point you will see that what was the path length for that point, and then the anomaly score will be the average of the path from the root to that node in all those trees. So that's why it's like a forest of all those isolation tree. So so as I said, the idea of isolation forest is like that. So it's idea, or maybe the concept behind it is like random partitioning produce shorter paths for anomalies. So that's like a maybe idea number 1. If you partition the data randomly, the paths for anomalies will be shorter. So when a forest of random tree collectively produce shorter path lengths for particular samples, they are high likely to be anomaly or outlier collectively together, all those trees. And the average path length, which will be the average number of split required to isolate a point, converge with the increase in the number of trees. So that's the concept number 2. It's saying that per tree you might have different paths, but if you have enough trees, then we can say the average of them would be something like it will converge to a number. So as you can see here, on average, the blue lines achieve a much larger path than the red one. So It's on the basis of the idea that isolation first is able to separate anomalies from like anomalies. So from the normal point. So that's kind of like a good like representation of how you can compare like maybe isolation tree and isolation forest, which will be a combination of lots of isolation tree. This technique is actually super I would say powerful as well. They're using it in different places. So the whole idea and concept is kind of similar to random forest, which they're using it for classification. Here, isolation forest is a symbol of all the isolation tree, and it has been used for finding anomaly and outlier in your data by just making lots of subspace in your data. And if I want to just go through these algorithm again, isolation first fork. We think that isolation first works best when small sampling size is used. So when the sample size is large, the normal instance are too close to the anomalies. So the number of partition required by each isolation first will be like will increase when the sample size is large enough, because like when you have lots of samples, to be able to isolate the node, the number of branch and number of the size of tree will grow as well. So that's one of the drawbacks if you want to just use isolation tree. So that's why isolation first it will just train based on some sample of a data per tree. So it will grow, as I said, it will grow the individual tree on different subsample of data. So basically, at the beginning, it will subsample from the data, and then it will create one isolation tree for that. And for the second isolation tree, it will subsample again randomly, and it will train isolation tree based on that. So, and once you have that some subsamples data, then it means then the branching process of the tree occur by selecting a random dimension or feature of the data. So basically, you're, as I said, randomly selecting some samples, and then you're randomly selecting a dimension or feature, and then within that dimension, you're randomly selecting a value within the minimum and maximum for sure, and then you will make a cut, and then you will split it in two separate space. So, and the process of branching is performed like recursively over the data set until a single point is isolated, or a predetermined depth limit is reached. And in the case a point runs, so when a tree goes like too deep, the branching process will stop, and it will assign maximum depth value to all those points. So it means like if you pick lots of sample and all of them happens to be normal, and even if you cut it, split it lots of time, if you can isolate it after reaching the depth limit that you have to define for your isolation first, then that tree will stop and say, okay, maybe none of them are maybe anomalies. So it will assign the maximum depth value that you have defined. So that's kind of like the whole idea of how Iforest is working. Basically, by, as I said, randomly subsampling data, randomly selecting a dimension, and randomly selecting a value within in that dimension, and try its best to be able to isolate one point in that tree. And then aggregation of all those three will be the definition of how Iforest is working. And based on that, you should be able to find anomaly in your data. The other algorithm for finding anomaly is one-SVM. As I said, like isolation first, the idea was anomaly point will be in a low density area and you should be able to cut it easily. Here, the idea is like a one-SVM. It's like you have just one class in your data. So as we have seen, it will be categorized as semi-supervised learning. So kind of the different. So the assumption here is like you have basically one class in your data, and that's why. So that's why you don't have the class A or class B. You have just class A, and the only thing that you want to do is to find a boundary around it. And to be able to find the boundary around it, you're looking for maybe a hyperlane that can, or a line that can separate all these, or kind of like a, you can find a boundary around all these points that you have in your space. And this algorithm can kind of learn a soft boundary in order to cluster the normal data instance as well. So sometimes then it will kind of make it to be a bit unsupervised as well. It means if you know you have some anomalies in your data as well, instead of using, as I said, hard boundary, you can use you can use soft boundary. It means you're allowing some noise to be present in your data, which basically here saying that, okay, you can just ignore maybe some point which is noise in my data, which will be kind of like an anomaly, and then find a boundary around the data. So as I said, the SVM are called large margin as well, because the underlying algorithm tried to identify the hyperlane that best represent the largest separation or margin within borderline data points. And one class SVM create a closed normal data boundary, as I said, and in this case find the maximum gap or maximum gap hyperlane that separate data from the origin. So that's kind of like a basic idea of one-SVM. It's like in regular SVM, you have two classes, and you want to be able to separate them in a way that the gap between these two classes is maximum. Here, you don't have the second class, you have just one class, and you want to kind of find a hyperlane that will maximize the gap between the origin and all the points that you have. And basically, that's how one-SVM is working. So, and a very nice property of SVMs is that it can actually create a nonlinear decision boundary as well by projecting the data through a nonlinear function called kernel to a space with a higher dimension. That means that a data point which can be separated by like a straight line in the original space are kind of like lifted to a feature space where there can be a straight hyperlane that separate the data points. So by using different nonlinear function, it can be just polynomial, it can be RBF, it can be any kind of function. They're usually using RBF. Then you can kind of map it to a different space that you can easily separate them. And here, the same thing happened as well. That we will, even for the workshop, during the workshop, we'll try different kernel, which is basically that nonlinear function, to project the data and see what will be the effect of it and which kernel will be best for our own data.